All right, now we're going to solve the first problem on test 1, problem 28. So as you can see, problem 28, we had a copper pipe and aluminum measured by an aluminum tape, both with a length of 18 meters. So the first part of this problem asks us to calculate the change in length due to thermal expansion of the copper pipe. So the coefficient, the thermal expansion coefficient for copper is given in the problem, 17 times 10 to the minus 6 inverse Celsius. The initial length of the copper is 18 meters. The initial temperature of the copper is 20.1 degrees Celsius. Now, you could do this in Celsius or Kelvin, it doesn't matter. I just went ahead and converted it into Kelvin. So 20.1 Celsius is 293.3 Kelvin. Temperature final, given in part A, is 303.6 Kelvin. And what we're trying to solve for in part A is the change in length of the copper. All right, so now that we've written down everything we know, let's solve the problem. So first we need to use the right equation, which in this case would be the thermal expansion equation, which is, so the change in length of the copper is equal to the thermal expansion coefficient of the copper times the initial length of the copper times the change in temperature of the copper. So let's write in all those numbers. So we've written in all our numbers for each quantity. So if we plug and chug those numbers, we'll get an answer of 3.2 times 10 to the negative 3 meters. So this is the change in length of the copper. Now let's start part B. So again, we will write down what we know. So in part B, we're asked to consider the thermal expansion of the aluminum. So coefficient of thermal expansion for aluminum, 24 times 10 to the minus 6 inverse Celsius. Initial length of the aluminum, 18 meters. Temperature initial of the aluminum, same as the initial temperature of the copper. Final temperature of the aluminum, same as the final temperature of the copper. So now let's solve the problem. So we use, again, our change in length equation for thermal expansion. So let's write in our numbers here. So we placed in all our numbers. Now let's plug and chug and find the final answer. And you get a final answer of 4.4 times 10 to the negative 3 meters. All right, part C is the tricky part. Part C is asking us what length the aluminum tape now measures for the copper pipe. So I've drawn a little extra stuff on the board here. So you'll notice when you do the problem that from parts A and B that the copper pipe expands slightly less than the aluminum tape. As I've noted up here on the board, again, these drawings are not to scale. So there's some difference in their length now. Used to be they were the same length, 18 meters, but now since they've heated up, they have a difference in their length. So how do we calculate that difference? Delta L measured would just be equal to the change in length of the aluminum minus the change in length of the copper. So again, this was 3.2 times 10 negative 3 meters minus 4.4 times 10 to the negative 3 meters. And we end up with an answer of negative 0.00050 meters. Very small difference, but still a difference nonetheless. So, but that's not the final answer. The final answer asks us, what is the final length measured by the aluminum tape? Well, we know that delta L measured is just going to be equal to the final measurement minus the initial measurement, right? So then our final measurement, so this is the length that the aluminum tape measures for the copper pipe, would be our delta L measured. So delta L measured plus our initial length. So we end up with this being 17.9995 meters, which is basically equal to 18 meters. And that's the final answer. All right, now we're going to solve problem 30 on test 1. In problem 30, we have an ideal monatomic gas that is isothermally expanding at constant temperature. So remember, isothermal means we have a constant temperature, so our change in temperature is 0. T initial equals T final. I'm just going to call that T. Equals 630 Kelvin. We're told that our initial volume is 0.510 meters cubed. Our final volume is 1.25 meters cubed. Our initial pressure is 1.16 times 10 to the 5 pascals. And just to give you the ideal gas constant, is 8.31 joules per mole Kelvin. All right. So in part A, we're tasked with finding the work done on the gas. So we need to use the expression for work done on the gas in an isothermal process. That's equal to minus nRT times the natural log of V final over V initial. And as you remember from class, we can take that negative inside the natural logarithm and just flip the fraction. So you notice here at this point that we know the ideal gas constant, we know the temperature, we know V initial, and we know V final. But notice we do not know what the number of moles are. So how do we solve that? How do we find number of moles? Well, we just use the ideal gas law. So we know P initial, V initial, and that's equal to the number of moles times the ideal gas constant times the temperature, which is the same both finally and initially. So we can solve for number of moles. So if you plug in the numbers, you'll get 11.3 moles. So now we can go back to our work expression and plug in the numbers. So work is equal to 11.3 moles times the ideal gas constant times the natural log of V initial divided by V final. So we plug in the numbers here. We get the work is equal to minus 5.30 times 10 to the 4 joules. So that is the work done on the gas. And that makes sense, right? Because we're expanding. The gas is expanding So the work done on the gas should be negative. In part B, we're asked to find the thermal energy transfer, or the heat that's transferred in this instance. So you remember for an isothermal process that heat is equal to minus the work done on the gas. And that makes sense, right? For the gas to expand, heat had to be added into the system. In part C, we're asked to find the change in internal energy. So you can recall that delta U is equal to Q plus W. That's the first law of thermodynamics, which would be 0. You could also just recall from the definition of an isothermal process that the change in internal energy is 0. And that is problem 30. Alright, let's solve problem 33 on test 1. So in problem 33, we have a charge that's enclosed by some surface. And we have an electric field to that charge of 10 newtons per coulomb. So it's not really stated in the problem, but we can imply that because this is positive, we're having electric field lines coming out of the surface, which means we have a positive charge inside the surface. The cross-sectional area of the surface is 5 meters squared. We're told that the angle theta between the normal vector, or area vector, and the electric field vector is 20 degrees. So our goal in this problem is to find the value of this charge enclosed. So how do we do that? Well, first we need to find out what the electric flux is. Electric flux is equal to the electric field magnitude, the area, cross-section area, times the cosine of the angle between the electric field vector and the area vector, which in this case is 20 degrees. So let's plug in our numbers here. And we'll end up with a flux of 47.0 newtons meters cubed per coulomb. So we found our flux, but that's not the end of the problem. We have to find out the charge enclosed. So in order to do that, we can use Gauss's law. So the flux is equal to the charge enclosed divided by epsilon naught. So we just rearrange this equation to solve for charge enclosed. And we'll recall that epsilon naught is equal to 8.854 times 10 to the minus 12 coulombs squared over newtons meters squared. So we get a value for the charge enclosed. That's 4.16 times 10 to the negative 10 coulombs. And that's how you solve the problem.